Hello there. We are very happy to have you all here. And to begin this seminar, I'd like to introduce you to the director of the UCAR Scientific Partnerships and Services Center, as well as CPAESS, Hannah Moriello.
Thank you very much, Dawn, and welcome everyone. We are delighted to have you attend the CPAESS Discovery Seminar Series. CPAESS scientists do everything from explore our ocean's depths, to fly into hurricanes to take critical measurements, to heliophysicists modeling coronal mass ejections, to those who unravel the mysteries of the Arctic. And we want to share this with the public, the NCAR UCAR community, and our many colleagues at universities across the globe. Just to orient you all, we are using Slido located below the presentation screen so that you can pose questions for our speaker at any time during the seminar, and they will be answered after the presentation. It is now my sincere pleasure to introduce to you today's speaker, Dr. Wenhao Dong, who is a UCAR CPAESS project scientist working with the Geophysical Fluid Dynamics Laboratory, GFDL. He specializes in model diagnostics and serves as a core member of the NOAA Model Diagnostic Task Force, MDTF project. Currently, he is responsible for model diagnostics in the post-processing of the next generation GFDL model. Wenhao received his PhD in atmospheric sciences from Tsinghua University in 2018. Today, he will be speaking on simulation of mesoscale convective systems using GFDL's new high-resolution general circulation model. Please join me in welcoming Wenhao.
Great. Hi, everyone. My name is Wenhao, a CPAESS project scientist working at GFDL. I'm very delighted today to be here to present my recent works on the mesoscale convective system using GFDL's new high-resolution 50-kilometer, 25-kilometer AM4 model. Before I begin, I would like to express my gratitude to my co-authors on these projects, as well as the valuable discussion from my colleagues here in GFDL, and also the insightful review comments from Dr. Michelle Moncrief from NCAR. So here's the overview of my presentation. I will start by explaining the motivation behind these projects, and then followed by two pieces of our works, separated works. One focuses on the tropical mesoscale convective system, the other one examining the MCS over the United States. And finally, I would like to discuss with you some of the questions that arose during our research. So MCS play a crucial role in our climate in many ways. There are several important reasons that why we want to look at MCS. First, they're responsible for a large fraction of precipitation and as well as the hydrological cycle. They can produce intense rainfall rates leading to flash floods, repletion water resources, and has a strong influence on local or on regional or global precipitation patterns. The figure on your right-hand side shows the fraction of MCS-related precipitation. We can see that over the tropics, the MCS contribute to around 50% of the total precipitation, and particularly over regions like Africa, the maritime continents, South America. Those fractions can be as high as 70%. In addition to the intense precipitation, MCS can also generate severe weather phenomena like the severe thunderstorm, tornadoes, wind gusts, or hails. So these examples are based on the quasi-linear convective system, which is one kind of MCS. We can find that those kind of systems are always accompanied by several different severe weather systems. As a rain-bearing system, the efficient rain-bearing system, MCS are also responsible for the global energy and heat redistribution. The figure here shows example of the MCS related latent heating. which we can find the top panel shows the zonal distribution, and the second panel shows the spatial distribution. We can find out that the MCS are responsible for those high percentage or the high latent heat radiating over not only over the tropics but also over several different regions where the MCS are most active. So given this importance, MCS has been studied for a really long time. So there's a lot of paper. I think back in 1914, there's monographs talking about 100 years of research on mesoscale convective system, to me, which can be broadly divided into 3 types. The first type is focused on the observation, which either utilizing the satellite data sets or the field campaigns. Those observational analysis has generated a lot of classic studies on the mesoscale convective system. The second type involves the convecting permitting models such as WRF model, which are generally used for case studies or over a smaller region or a short period due to the computational constraints. For example, Dr. Andres Prim from NCAR has done excellent jobs in these fields. While the third category involved the use of GCM, which were not considered capable in simulating MCS previously, but with the horizontal resolution approaching below 100 kilometers, scientists have started to look at MCS simulated in these models. So here shows 3 examples from recent studies, which are based on you can find out that those resolutions are pretty high, ranging from 50 kilometers to 25 kilometers. In addition to the high horizontal resolution, people are trying to use super parameterized model to look at the simulated MCS, and also come up with some other parameterizations. For instance, the multi-scale coherent structure parameterization developed by Dr. Moncrief has been used in a lot of studies, which has been proved to be able to simulate MGO, tropical waves, and associated precipitation pretty well. But if you look closely to these 3 simulations, you can find even we have higher resolution. For instance, based on the CAM5 model, even we increase the resolution to 25 kilometers, we still have here shows the occurrence frequency of the MCS. You can interpret as a number of MCS. There's substantial underestimation of MCS over Central US. The number is about 50%. While in those experiments involve the super parameterization, when you compare with the model without super parameterization, we see large improvements in terms of the MCS numbers. But when you compare with the observation, you still see a large underestimation. And also, by incorporating the MCSP scheme in the E3SM model, we can see in terms of the MCS related precipitation, there's not too much improvements comparing to the default model, which means there's more work need to do to examine the feedback or the coupling between different schemes in this model. But the point I want to highlight here is that if you look at those recent works, they are merely based on, or they're mainly coming from the NCAR model, CAM5, or the E3SM model. While in GFDL, nobody has yet evaluated the model's capability in simulating the MCS. That's a reason. That's the reason why we want to initiate this project to look at this type of weather events. Though we haven't done a lot of work on evaluating MCS, but we have considerable experience looking at other systems. For instance, we have looked at the simulation of tropical cyclones. Here shows the results based on one of GFDL early model, HIRAM, which is a 50-kilometer AGCM. So you can see here the spatial distribution of the tropical cyclone tracks, as well as their seasonality and interannual variability, are reasonably simulated by this model. In addition, we also take a look at the atmospheric rivers simulated in this model. This time we are using the NATIS 50-kilometer GFDL AM4 model. You can see for the spatial distribution of atmospheric rivers in both cold season and warm season are well simulated, and the probability distribution function of several key features, including the size, orientation, intensity, are captured pretty well in this model. So given this model's capability to simulate the weather features like the tropical cyclone and ARs, and considering that the comparable scales, for instance, between the tropical cyclone and MCS, we are curious to see if this model could capture or simulate the MCS. So here's the data and masses used in these projects. With the observation is based on the clouds datasets covering 1985 to 2008, which provides 3 hours, 33 kilometer brightness temperature. Well, to evaluate the model, we conduct simulation during the present day, which cover the same periods, which provides 3 hour, 50 kilometer OIR. So the first step for us is to convert the model's OIR to brightness temperature. We basically follow the previously established relationship between these two variables, and we converted the OIR to the brightness temperature. After that, we apply a two-step algorithm that is designed to identify the MCS based on two thresholds. First is the brightness temperature thresholds, and the second one is the minimum area coverage thresholds, which are set to 2033 Kelvin and 50,000 square kilometers over the tropics. The values are slightly different over the US, which we'll introduce later. So we first examine the converted brightness temperature, because as I mentioned, we need to convert the OIR to the brightness temperature, which is input for the MCS tracking. So here, the first panel shows the observed brightness temperature, and the second panel shows the converted brightness temperature for the model simulation. And the panel C shows their differences. So generally, we can see that the model well captured the observed brightness temperature distribution pattern with a pattern correlation as to be 0.93, and the mean bears to be 1.7 Kelvin. But we can also notice that over certain regions, for instance, the Western Pacific or the tropical subsidence region, we see that the bears can be as large as 5 Kelvin. And the right panel shows the MCS occurrence frequency. So consistent with the brightness temperature, we can see that the model generally capture the spatial distribution, though we see large bears along the Andes Mountains, and there's an overall slightly overestimation over the whole tropics in the model. And then later on, we examine the seasonality and the interannual variability over different continents, regions like Africa, Maritime continent, tropical Americas, and also several different ocean basins. And here are the results. On the left-hand side shows the seasonality of the MCS. The black curve is from the observation, while the blue curve from the model simulation. So in terms of the seasonality, the model well captured the seasonal evolution in all those regions except for the Indian Ocean, which shows opposite results. The simulated seasonality is out of phase of the observed one, which might be due to the AGCM, the atmospheric model with the prescribed SST, which fails to capture, the strong air-sea coupling over the Indian Ocean. Well, in terms of the interannual variability, what we can find is over the ocean, the letter phi, which shows a much larger correlation coefficient than the regions than the continental regions. This may indicate that over the land, the variability of MCS are also subject to the air-land interaction or other, land processes. So these are the mean features. We also conduct some statistical analysis on event basis. Here shows the PDF of the MCS duration, intensity, and size. So again, the black one shows the observation, while the blue one is from the model simulation. So from this figure, we can see clearly that the simulated MCS tend to last longer, and also the size will be larger in the model simulation. But usually at the meantime, the simulated MCS are weaker compared to the observation. So here the intensity is measured by the mean branch temperature average over each of the MCS. Despite those differences, we found a robust relationship between the MCS size versus duration and MCS size versus intensity. That is, the MCS size tend to be larger when the MCS lasts longer, and also if the MCS that are stronger or are more intense. So those are verified in two representative regions. One is from Africa, the continental region, and another one is from West Pacific. Both regions show most active MCS occurrence. And this relationship holds true even when we switch from all the samples, the mean, to the top 5 events. You can see those numbers, the dependency of the size on duration, the dependency of the size on intensity are generally consistent with these two different types. So based on these results, we found that this model is useful. Probably we can use it. We have some confidence in further using it to explore other questions. The first one we want to answer is the response of tropical MCS to global warming. The second one, we want to shift our focus from tropics to US, where we also experience a lot of MCS, and also, it's more complex. We want to evaluate this model over these regions. Regarding the response to warming scenario, we conduct 2 sets of simulations. The first set, each set of simulation contains each set of the experiment contains 2 simulations. So for the first set, in addition to the present day simulation, which is forced by the observed SST CS condition, we conduct a future simulation, which is forced by the Semi-5 model mean SST in RCP85 scenario. And in the second side, we conduct 2 sensitivity tests. The first one is a CLIMO. It's called CLIMO, which is forced by the 2010 climatology SST and CS and radiative forcing, etc. And the other one is the plus 4K, the 4K experiments, which is forced by the same condition, except for we add a uniform 4K increase in SST. So when we compare the FU experiments simulation with PD simulation, we can study the SST pattern on the impact of SST pattern on the projected as MCS. While when we compare the 4K experiment with the CL experiment, we can learn the impact of the mean SST on the simulated MCS. So here are the results based on these 2 sets of experiments. Here we focus on the difference map here. On the left-hand side shows the future minus present day simulation. What we can find is significant reduction over Africa, Indian Ocean, the Pacific subsistence region, and Amazon regions. And both results are normalized by the respective global warming. So they're on the same units. Well, on the right-hand side shows the difference between the 4K experiment and the control simulation. We can see they share much similarity with these results over the continents. We, in this experiment, in this difference map, we see the reduction over all the continents. And we also see the increase over the Western Pacific subsistence regions as well. But there are differences over the Indian Ocean. We compare these two differences. So here is a quick summary for the first part of the first piece of the work that we evaluate the model in simulating MCS over the tropics and also try to examine their response to global warming. So what we learn is that the spatial distribution, seasonality, interannual variability of MCS over different land and oceanic regions are reasonably simulated in this 50-kilometer AM4 model. And second, based on event scale analysis, we found the duration, intensity, size of the MCS are well captured in the model, and also the linkage among these three variables are consistent between the model and the observation. Specifically, longer lived and stronger events, MCS tend to be larger. As to the global warming scenario, there's an overall decrease in the occurrence frequency of tropical MCS, with a more pronounced reduction observed over lands compared to over the ocean. So next, let's shift our gear to the US. So we apply the same analysis to over the North America, but we use the values are different. So first, for the temperature, the brightness temperature threshold, we reduce it to 221 Kelvin, and for the size, we increase to 30,000 square kilometer. Those two values have been widely used in previous studies over the US region. So here shows the MCS occurrence frequency. Given the large difference between the spring and summer season, we divided them into two periods. One is cover April to June, the second one covered July to August. So the first row shows the observation, the second row shows the model simulation, and third row shows their differences. So when we compare the spring season or early summer season with the July to August periods, we can see we have more MCS occurrence frequency in both observation and model simulation. When we contrast the model simulation with the observation, we notice negligible differences over the central US, which is denoted by the dashed line here. But we found a significant positive bias in the model. That means the model simulated too many MCS over the eastern US, which we will discuss in details later. So we also examined the seasonality and the interannual variability of MCS over the central US. Similarly, similar to the tropical regions, the model could capture the seasonality of the MCS pretty well over central US. But in terms of the interannual variability, we can find though the mean number of MCS are comparable between the observation and the model, they are weakly correlated with each other, which again may indicate that the MCS over the continental region may subject to air-land interaction or other land processes, which is much more complicated than over the tropical oceans. So we forgot to mention that we're using 3-hour brightness temperature data sets, so which enable us to also take a look at the diurnal cycle of MCS over the central US, which is pretty important because it is well known based on the ground's measurements or observation that MCS over the central US are usually generated to the east of Rocky Mountain in the late evening or midnights. So indeed, our results confirm that based on the brightness temperature confirms that the observed MCS tend to generate. So here, this is the genesis of the MCS based on observation. the observed MCS tend to generate at light around 21 late evening, and becomes activates. This is occurrence frequency, becomes activates and persists into the early morning hours through the warm season in both the April to June and July to August. And we can see from this map that the gradually increasing peak timing indicates the eastward propagation of the MCS in observation. However, in the model simulation, the simulated MCS over this region are generated in the morning hours and becomes activates around the dawn time. So the diurnal phase of the MCS in the simulation is totally misrepresented in this model. And we also check the features, the duration, intensity, size, and the translation speed of the MCS over the central US, consistent with the results over the tropical regions. In this model, the blue curves, blue bars, show that model the simulated MCS tend to last longer with a weaker intensity, the larger the brightness temperature, the smaller the intensity, and a larger size. And for the translation speed, I would say they're comparable between the observation and the model simulation. And moving forward, we explored the favorable large-scale circulation patterns over the US on the genesis of MCS over the central US. Here shows the observed. So here the shading shows the geopotential heights, and the contours here shows the equivalent potential temperature. So the larger the moisture or the warmer air parcel is, and then the vectors represent the horizontal winds on 3 different layers: 250 hectopascal, 500 hectopascal, and the surface 850 hectopascal. So the first row and the third row are based on the observation in 2 different periods, and the second row and the fourth row are based on the observation. So there are several distinctive features. One is the Great Plains low-level jets, which is indicated by the strong southerlies near the surface. You can see the arrows here, which brings the moisture, the moist air parcel into the Great Plains. And then the another feature is the trough and ridge system, which can be seen from the geopotential height or the wind vectors as well. This may be more common to see from the anomaly fields. So the right hand side is basically the same as mean as the left hand side, but there are anomalies within the periods like April to June or July to August. So we can see this trough ridge system, which persists in all 3 layers, and also the strong low-level jets over this region. So put them together is like when the MCS prefers to occur when strong low-level jet brings the moist air into this region, and which those moist and warm air ascends over the central US, moisten the whole troposphere, which favor the development of MCS. Well, compared to the April to June, to the spring to early summer, the results based on over the July to August are slightly different compared to the spring season, because the jet moves northward, and you can see those contours, those anomalies becomes shifts poleward and becomes broader distributed. And when we compare the model with the observation, the model seems to in good agreements with the observation during the spring season, but we still can see large biases over the near surface or in the lower level, where the positive anomaly extends all the way to Canada, which is not the case in the observation, and Also, in the model simulation, the positive anomalies are usually larger than the negative counterparts. And those distorted simulation of the lower level is more obvious in the summer season. So at last, we try to look at the associated precipitation because we want to. There's a hypothesis we want to answer. So can the MCS-related precipitation explain the simulated long-standing dry bears over the central US? Because in the past few generations of CMIP models, which the resolution are pretty high, which could not is pretty coarse, is larger than 100 kilometer, which are not capable to simulate MCS. So we want to see if those dry bears are associated with the failure in simulating the MCS. So here shows the results. The first column shows the total precipitation based on the observation model in 2 different periods. And the second column shows the MCS related precipitation. And if we focus on the difference, this panel shows the mean total precipitation in spring. You will see there's slightly dry bears over the central US, but for the MCS related precipitation, we do not see strong signals of the negative anomalies in precipitation. While in summer, that's when the model has the strongest dry bears over the central US. You can see here, but the MCS related precipitation, we do see a small dry bears over the central US, but comparable to the mean precipitation bears, this is much smaller. And this is true when we take a look at the MCS related precipitation average over the central US. We take a look at the PDF. You can see there are some differences between the model and the observation, but overall the model are comparable with observation. That indicates the MCS related precipitation could not explain the dry bears staying over the central US. So the land MCS related precipitation may play a significant role here because the magnitude may be even larger than the MCS related precipitation. So summary for the second parts, when we apply the same methods to the US region, we found that the spatial distribution and seasonality of occurrence and genesis frequency of MCS is reasonably simulated over the central US. So here we just focus on the summary is is generated over the central US in both seasons, and the model reliably reproduce the key features of MCS, including the size, intensity, duration, as well as the translation speed. And as for the favorable large-scale circulation patterns associated with the MCS, they are well captured in the model during the spring and early summer, but the bears becomes larger in summertime. Those are the positive parts for the model in the US region, but we also noticed several things that need further improvements. First, that we see the spatial distribution, we see dramatic bears, positive bears over the eastern US. And second, the model totally misrepresents the amplitude as well as the phase of the diurnal cycle of MCS during both seasons. And third one, which is mentioned that the large-scale circulation patterns are misrepresented in the model, especially during the summertime. Well, as for the MCS-related precipitation, we found that though the MCS-related precipitation shows some consistent signals as the total precipitation bears, but this bears is insufficient to explain the significant dry bears observed in the total precipitation of the central US, especially during the summertime. So here is a discussion because this project is we just started this project and we got more questions than answers during this research. Something we want to discuss is, first of all, the dramatic positive bears over the eastern US is really concerning. We've found, because if you compare with the mean state, is larger than 50% compared over the eastern of the US. But when we look at the spatial distribution, we found that the bears seems to be concentrated around the Appalachian Mountains. You can see here, this is where the mountain is. Probably I can draw the contours here. So it's always the positive bias is larger on the southeastern side of the mountain. So we're thinking either the moisture field of this region, or the circulation patterns over this region is not well simulated compared to the observation. We take a look at the low-level distribution of the specific humidity, as well as the low-level wind fields. The left-hand side shows the mean fields, and the right-hand side shows the anomaly. Those are composite on the MCS generated over the central US. So in these two seasons, we can see stronger southerlies, moisture air over the central US, which favors the development of MCS over the central US. But when we compare the model with the observation, we see sort of the tail of the larger moisture loading over the eastern US, which may be useful to explain the observed positive bias. And also you can see those the westerlies is weaker in the model. We want to know if those differences, or to what extent those differences may contribute to the observed positive bias of this region. Now, what we are trying to do is to conduct a nudge simulation. We nudge the large scale, the wind fields, and trying to see if these bias will be reduced. If yes, maybe we can conclude that the wind fields are important for the MCS simulate of this region. If not, then probably means some other processes may play a crucial role here. A second question that we don't touch in this analysis is, because we know there are several different types of the MCS, like shown here, there are like more than 5 different types. I think there are more than 5 types of MCS. And also the sound-wise circulation pattern embedded in the MCS. This is the most, I would say, distinct feature of the MCS, distinguish MCS from other weather system. But we think in 50-kilometer model, we could not resolve those details. We have tried to look at the composites. We do see some features, but we don't have confidence to resolve those circulation patterns in the 50-kilometer model we're using. Our plan is to, now we have conducted another simulation based on 25-kilometer AM4, and in GFDL we also have the storm resolving model, which is running at 3.5-kilometer resolution. We want to use these two simulations to look at first the different types of MCS, and second, the more like the embedded structure of the MCS, especially the sound-wise circulation patterns. And the third thing is that currently the tracking of MCS is merely based on the brightness temperature. In the model, we convert OIR to brightness temperature. But later on, we found out, so here on the left-hand side, what we are showing is the shading shows radar reflectability, and the contours shows the surface precipitation, and the vectors shows the 700 hectopascal winds. This is for a typical MCS case, which is propagated from westward to eastward. And on the right-hand side shows the same case, but the shading here shows the brightness temperature. The contour here is still the precipitation. What we found is that though overall the brightness temperature corresponds well with the radar reflectivity, you can see it's much more smoother based on the brightness temperature. One possible reason for this is that for the radar reflectivity, it's more like an instantaneous measurements, well, or over short periods. But for the brightness temperature is the brightness temperature from the clouds datasets is the 3-hour average, which may smooth out a lot of details. Now we have what we have is the high spatial and temporal frequency of precipitation. So that's why we put those contours here. You can see on this map, we can see the radar reflectivity corresponds pretty well with the surface precipitation. But a similar thing does not, there's always mismatch of the brightness temperature and the surface precipitation. I think this is understandable because the winds, advance the precipitation or, shifted downwinds a little bit. And so there's a mismatch between the brightness temperature and surface precipitation. So what we are trying to do is that we try to include the surface precipitation as another constraint for the MCS tracking. So in this way, we may provide another constraint on the tracked MCS, because we are trying to say if this will help us to reduce especially the positive bias over the eastern US, we want to know which parts could contribute to that differences. Those are these 3 questions that we are trying to address now. As I mentioned, this is an ongoing efforts. If you see any interesting, things among this research, or you think there's a room for collaborations, I would be really happy to have your feedbacks. I think that's that's all I have today for these 2 pieces of work. I'm happy to take any questions.
Thank you so much for sharing your great work with us, Wenhao. We truly appreciate it. Now to our Q&A portion of today's seminar, and I would like to direct everyone's attention to the QR code on your screen. Please enter your questions here for our speaker. While you're doing that, I would like to invite you all to attend our next seminar on Wednesday, August 23rd, 2023 at 11 a.m. Mountain Time, when CPAESS program specialist Dr. Anne-Christine Zinken, working at NOAA's Global Ocean Monitoring and Observing Program, GOMO, will be speaking.
Okay, and it looks like we do have an initial question here. Thank you for your explanations of your work. What future approaches would you like to take to improve the model even further?
Great question. I think the first few steps for us is look at, as I mentioned, we're looking at higher resolution model, 25 kilometer, which will be our model for the next generation of CMA 7. We're looking at this 25 kilometer. In addition, we're looking at the global storm resolving model, which is a 3.5 kilometer simulation, but over a very short periods. In addition to those higher resolution, we are trying to, 2 things we have done is to include the so-called non-local buoyancy effects in the model. Another one is a different closure scheme for the shallow accumulators. We're now actively testing these 2 approaches to see if there's any improvements in the simulating of MCS.
Excellent. Thank you, Wenhao.
Yep.
We have another question for you. Any further thoughts on why there is a decrease in MCSs over land in future trends? And I'm especially interested in your response for Africa. Thank you for the question.
Yeah, that's what we are working on right now. I think the general idea is that based on the Held and Soden framework, in the warming scenario, the P equals, I just want to explain the equation. The precipitation equals the mass flux times the specific humidity, or you can think about the mixing ratio. And the mixing ratio will increase at 7% per Kelvin increase, while the precipitation we know is much slower. So that means the mass flux will be reduced. So that's where the general idea comes from. Then we don't lead, so the mass flux, the Africa, maritime continents, and South Amazon regions are three dominant ascending regions. So we see those reduction over all those ascending branch, which may be linked to the decreased mass flux in the warming scenario. But now we want to try to come up with some index to represent those, these ideas. We look at the different metrics, usually used for indicate the MCS or the deep convection, like the cape thing and the wind shears, all the different things. What we found is that in the warming scenario, actually every index increase. But what we notice that is the cape, especially the cape, you will see a much slower increase over the length. But for the thing, that's the inhibition energy, there's a large increase over the length. That means though the available energy for convection increase in a warming scenario, but it's much slower, and we got a stronger inhibition over the land compared to the ocean. So that we're trying to come up with index based on those features to represent, the overall reduction over the continents.
Thank you so much, Wenhao. Folks, do please enter any questions that you have. Wenhao, is there anything else that you would like to just kind of add concerning this in general for?
Yeah.
folks? Yeah.
Yeah, of course. I mentioned in one slide that in the past 5 years, there comes up those studies working at the MCS in the GCMs, and mainly using the the NCAR CAM5 model and also the E3SM model. I know there are several groups. One in the LNL and the PNL groups are working on this activity. What I want to know is that if any people at NCAR can provide us if you're interested, you have a simulation like 25 kilometer or 50 kilometer that you want to collaborate, I would be really happy to do that. The reason for that is our method, the tracking methods, and the converting relationships, all the things may contribute to the differences between our work and the previous studies. So what I want to say is that we could come up with a comparison efforts that if we have the NCAR simulation based on CAM5 or whatever you have, that we have AM4 model, we can use the same tracking algorithm. We will apply the same algorithm, then we can compare what's the difference coming from, right? If we want to see if the difference over the Eastern US are just in our model or is due to the different tracking algorithm. Because based on the previous study, there's overall underestimation over the entire US based on the CAM5 model in the E3SM model. It's totally different from our simulation. We want to know what's the reason behind that. So if anybody interested in that, you have a simulation that favors these efforts, please contact me.
Thank you so much, Wenhao, and I hope some of our scientists do reach out. I don't see any questions coming in yet. Just so that everyone knows, this will be posted on YouTube soon also. If anyone has any questions, please submit them. Otherwise, we might just wrap it up for today.
Yeah, if you have a question later on, feel free to reach me.
Great. Thank you so much, Don, and thank you again, Wenhao, for a great seminar. In closing, I would like to thank you all for coming to this UCAR.CPAESS Discovery Seminar and remind you to go to our website to find out future talks at cpaess.ucar.edu. Here you will be able to find a link to this talk after it's uploaded to YouTube as well. Wenhao, our sincere thanks to you for sharing your important research with us. I also want to take the opportunity to thank Jesse Webb of UCAR Multimedia Services for his invaluable assistance, and to our own Don Mullally and Alex Meyer from UCAR.CPAESS for the planning of this seminar. I hope to see you for our next CPAESS Discovery Seminar on Wednesday, August 23rd. Good afternoon, everyone.
Yeah, thank you for organizing this.